Good evening and welcome to the January program for the Madison DX Club. And tonight's program is by Professor Fred Archibald, VE1FA. And Fred has spoken to our group before, and we expect tonight's program to be just as interesting, if not more interesting, than his program on the Titanic. So, Fred, if you're ready, let's all learn about the Gibson Girl.
This evening, I'd like to speak about what used to be called ASR, or Air Sea Rescue, and how it was used in World War II, and the Gibson Girl transmitter, and how it got its name and what it did. Air Sea Rescue, really from the beginning of the war in Britain, was given very high priority, and as the war went on, a lot of resources. There's three very good reasons why. One, the British had a 30 flight system, and the US had a 25 flight, meaning that an air crew would, to finish off, to get out of the bombers and off the bombing program, had to finish 30 flights if they were British, 25 if they were American. And the chances, especially early in the war, when the bombers flew unprotected over Europe, of finishing 25 or 30 missions alive was very small. It was far less than 50%. It was, depending on the time, it was often in the 10 to 20% area. So the men knew this, of course. And so the first reason was that the Allies figured that they really had to show the men that were hazarding their lives like this were being given every possible opportunity to survive. Every tool, every trick, every bit of safety they could put on the plane and around the men was something which would raise morale. And as the war went on, at first, the Allies tended to be short of equipment. But as you may know, that, for instance, in 1944, the industrial output of the United States was greater than the rest of the world put together. So as we all know the story, that enormous numbers of ships and tanks and planes and every other thing that the war required were produced. And it became more and more clear that highly experienced aircrew were far more valuable than the plane they were in. And the third, of course, is simple humanitarian. They wanted as few men as possible to die in the air service. Here's some numbers, which I think are fairly accurate. I've seen numbers from several sources that are pretty close to this. And so in the European Theater of Operations, the ETO, the US 8th Air Force losses were 55,000 men killed and captured. Of that, and in addition to that, about 8,400 were seriously wounded. And the British Bomber Command losses were about 38,300 killed. I put in Canadian losses, being a dual citizen up here. And actually, the rate, Canada has about a tenth the population of the US. The rate was considerably higher, about 10,000 Canadian aircrew were killed, and other allies about 6,600. So these are huge losses. And when you look at the success rate, the early ASR was not good. That in 1939 to 40, about 12% of the men that were known to have gone into the water due to a ditching, about 12% survived, 1 in 8, 7 out of 8 died. By 1945, that had risen to 90% recovery of the men alive. And how many were saved? In Europe, British and US, it was about just under 2,000 aircrew were saved. And in the Pacific theater, close to the same, a little less, 1,841 were. So the ASR in the end, in both theaters, saved almost 4,000 aircrew. Here's an example of another plane, another B-17, which actually made it back to England. You can imagine some of the ones that didn't make it back to England, but this, it's a little sad to look at this because in this plane, the B-17, the radio operator's position is just about the middle of the plane, just forward of the explosion. You see the torn metal. Now, he sat there, and I'm pretty sure he's not one of those fellows walking around outside. Here's another bit of minor damage. And I wouldn't want to have been the bombardier in this particular plane. But this is perhaps the drive home that a lot of planes attempted to cross the Channel or the Bay of Biscay or the North Sea, or what they called the Western approaches to get back to England, and didn't make it. A lot of men went into the water. And to look at it in a sort of hard light, in 39 to 41, if you were ditching, and particularly at night in fog or in foul weather, which one of the three was very often present around Britain, you would probably be unseen, unheard, never found, and dead within 7 days, and of course much sooner in winter. And that within 7 days assumes that you got into a raft. So it was a grim picture, and of course this didn't help the morale of the men at that time. So the Allied hierarchy, commanders, looked at the thing and said, hang on here. My apologies. Yeah, there we go. I just couldn't see the top line here. Actually, I still can't. What's going on? Okay, I'll get along without it. How do you know when men are ditching at sea? Planes don't come back from a raid. Were they shot down over Europe, or did they land in the sea? The second question was, how can you quickly locate and get to downed air crew? And the easiest, the best answer that you can come up with is a small portable transmitter. And this has been thought of that you can take into the life raft or the lifeboat with you and announce your presence and your location to planes and ships with direction finding equipment. But before the war, back in the early 30s, this was all thought of, and a variety of battery-powered radios were tried, and they were not successful. They were too heavy, and the battery typically had a very short life, so by the time you really needed it, it was dead. Or if it was good when you went into the drink, you might have to be using it for a week or 2 weeks, and the battery would go flat far sooner than that. The other thing was, it was often dead when it was needed because, of course, the planes at the time weren't pressurized and they weren't heated inside. And batteries, lead acid batteries and dry cells are of the old style that was used then, were immediately damaged by freeze thaw because of the very, very cold temperatures in the plane. So batteries just weren't a solution. A few were tried. The Germans had one, and the transmitter, the Ns2, weighed something like 75 pounds, and you're in a tossing sea and trying to get into a tiny rubber raft with a 75-pound radio. Anyway, it didn't work. Now this is a problem. I can't see the top couple of lines in my presentation here. Not sure if there's anything I can do.
Yeah, it looks fine here though.
Yeah, I just can't see it here.
Yeah.
This is really annoying. Oh, sorry. Well, I'll have to do what I can with it. So this is the Ns2, and this was just found in, I believe it was 1940, floating in the English Channel by an English patrol boat. And they saw a little yellow one-man raft in the distance, and they pulled up to it, and there was no man in it, but there was this yellow box, and it was clearly a German raft, and this was called the Ns2, which was the ancestor of what the Allies finally put together. And it was a hand-cranked generator, and it powered a 5-watt, 500 kilohertz transmitter. And this was built in Philips in the Netherlands after the Germans had taken it. And it was really a nice design in some respects. It had hand crank generator. You turned that handle on the top, and it had a box kite antenna to raise. And of course, for 500 kilohertz, you need a substantial length of wire. I think that their antenna was about 300 feet, which is what the Allied one was. But it had some severe shortcomings. The shape, the double concave curves, was for a particular purpose. You can't operate a radio like this with a crank without having it firmly attached in some way to something that's fairly stable. And the little rubber rafts that they had, which were basically very, very thin fabric, rubberized fabric blown up with a little CO2 cylinder, there's nothing firm or solid. So it had to be anchored to the pilot or the man or men who were in it. And they did that by, you place this between your legs with the reel of antenna wire you can see there facing outward, and you cranked. And this was better operated by two people, but one person could do it. But the Germans chose a speed for the crank. The generator inside turned at about 5,000 RPM, as did the Allied one that was developed from this. But the Germans chose a speed of 120 RPM. And of course, the higher RPM the crank goes, the less effort there will be to turn it for a given speed of 5,000 RPM in the generator. The trouble is that 120 is not at all comfortable for a human being. Ask me how I know, I've tried. And the Allies went down to 80 RPM, which is much more comfortable, a little heavier load because you've got a greater gearing up to 5,000 RPM. But the arm can maintain 80 RPM quite comfortably where it can't for 120. The Allies cut the weight from 29 pounds to 18 pounds, which was a huge help in handling the thing and tossing seas and flimsy rafts. This had no leg strap, and you held it between your legs. If you think what that means, that it means that the muscles in your inner thighs, which aren't particularly strong muscles, have to hold, in this case, this 29-pound box between your legs for an indefinite period while you vigorously crank the top. And the Allied version, which you'll see in a moment, had a great broad leg strap that went over those concavities. And it made all the difference because with the leg strap, your legs were held firmly against the box and you didn't need to use those muscles at all. So it made a big, big difference in the comfort and the ability to crank the thing effectively. Also, if the weather was calm, if you were a German pilot and you went in with the Ns2, there was no way to put an antenna up in calm weather. You had a box kite, which is a very efficient kind of kite. But remember, even I'm sure most of you have played with a box kite, probably not for a few years, but the box kite, normally you get it going by running across a flat field or along a beach. Well, you can't run across water, so you just have to hold it up and hopefully there'll be enough breeze to lift it. And there very often isn't. So it simply meant that the whole apparatus could only be used in certain weather, and that wasn't very helpful. Got to do most of this from memory because I haven't got much on the screen. So I think it was the T1333 that the British built was an attempt to copy this with a few improvements. But the problem was that in 1940 and 41, the Brits were in dire straits. They really had no resources. And so they went to the US and asked the Bendix company of North Hollywood to build it as soon as humanly possible. And okay, so what the Bendix Corporation of North Hollywood, California came up with is this device you see in front of you here. And they solved some of the basic problems very nicely. You see the great broad straps they have on the side there. So that the downed aviator, downed aircrew would simply sit down in this rubber wrap and he'd slide that big, it's about 5 inches wide, great broad strap around both legs. And there was a very nice clamp at one end. So it was very easy to do. And it was quite comfortable even after a long time because it was so broad, of course, it didn't cut into the flesh. And it made it much, much easier to crank. And it was in mass production by about May of 42. The request had come in late 41. And there were quite a wide variety of improvements over the Germans' NS2. one of the things that interested me about this was that it's filled with little things that show that in the development of this, Bendix, first, they built something that they thought was about right. And then they got the use of a large swimming pool in California, and they would throw it in, and then they would throw in an uninflated raft and ask their test candidate to jump in, and they would see how long and how effectively he could assemble a working transmitter. And when the thing was designed to the point where that was quite easy to do, they moved the whole business out into the Pacific Ocean. So they used real people attempting to get the system functioning until they had a system which it wasn't foolproof, but it was very well designed, at least in my opinion. So it was in mass production by 42. And by the end of the war, they'd produce 100,000 of these, which is why so many ended up in war surplus. But they were widely used, not just in planes, but many ships adopted them. They would put them in every lifeboat, and they get used in a variety of both ship lifeboats and aviation rescue rafts. Let me just get this up out of the way. Yeah, okay. Hang on to make it all the way up. Oh no, okay, here we go. So why are they called Gibson Girls? And the reason was there was a clothing designer named Charles Dana Gibson back. He was famous from the 1890s up to about the 1920s, and all his girls that he hung his clothes on had this hourglass figure. So if you know the young military minds, so that's what they thought of when they saw this hourglass shape of the radio. And oh yes, and also I should mention that later in the war, when it became more and more obvious that the equipment was kind of throwaway, but the men weren't, they developed special boats which strapped to the bottom of B-17s and B-29s and so forth, and they would drop a whole boat in to assist the men in the life raft. And the boat would, of course, have a Gibson Girl transmitter, and they produced about 100,000. There were other things which they could use to draw the attention of search teams to men adrift in rafts. And they had a sea dye, which would dye the sea orange, and smoke canisters and signal mirrors. But of course, none of these things were any good at night. And they were only good in the immediate vicinity of the raft. Although they were still helpful because the normal height that the search plane would search at was about 2,500 feet, being a compromise between the amount of sea you could cover in a given time and how small a thing you could see. So the other things did help, but the radio had the fundamental advantage that it worked just as well as night. And these Gibson Girls had a second function or second feature, and that was that you could switch from the radio to a light. And if you're trying to find a life raft at night, without a light in the life raft, good luck, you'll never find it. And the light can be very small, and you can still find it. Hang on. There we go. Okay, now there was two separate models made, and the first one was made for Europe, and it was called the BC 778, I should say the war in Europe. And the second one was made, I think they started in late 42. It was called the CRT-3 or 3A. To a casual glance, they look almost exactly the same, but there was an important difference. And what they realized fairly early on was that the BC 778, it was developed for the geography and the distances of the air war in Europe. And so with producing 5 watts of 500 kilohertz, and that being fed into a 300-foot woven bronze wire antenna with the ground of the ocean itself, it had a range of about 250 to 500 miles. And for the channel the North Sea, what the Brits called the Western approaches, the Bay of Biscay. This was plenty because you could go down anywhere in that area and there would be quite a number of radios listening on 500 kilohertz. And so your chances of being heard were excellent. I put out actually 5 watts of MCW, modulated CW, what used to be called 82. And there was a reason for this too, that if they just put out CW, then the radio had to have a BFO, and the BFO had to be on. If you put out modulated CW, any receiver can pick it up because it's modulated. And also you're putting out 3 signals instead of 1, as you know. The modulation was a 1 kilohertz audio tone. So of course you're putting out 499, 500, and 501, spreads the signal out for people who aren't on exactly the frequency that you're on. And of course, these things thrown into the sea and bashed around and pulled out and set up, they could be a little bit off frequency, although actually they were pretty stable. Now, for the Pacific, they realized right away that 500 miles might be okay around Britain, but the Pacific is, of course, the world's biggest ocean, and it was not. Most planes that went down, or many planes that went down, were many hundred or thousand miles away from rescue stations. So they made it basically a dual bander, if you like. It as you cranked it for 30 seconds of every minute, it would be on 500 kilohertz, and then it would shift over to a shortwave frequency. At first, it was 8280, which was an aviation emergency frequency of the time. But then they decided for various reasons that they would use a different aviation emergency frequency of 8364. So the early CRT3s will be the 8280 and the later ones 8364. And the 8364, or either frequency, with the 300-foot antenna, had a typically under conditions of the war, which was not the peak of the sunspot cycle, it could be heard up to 3,000 miles, at least at night. And think of 40 meters, the behavior of the band would be fairly similar to 40. And you could choose to run the 500 kilocycle alone or both alternating, which was what I think most people did. Now, there's some other interesting differences between them too, which hopefully we'll go to now. Okay, this is just looking at the top of the control panel on the front. Actually, let me just go back and point out some of the things on this machine so you get a layout here. The crank, of course, goes in the top and goes into a big gearbox inside, which converts your 80 RPM to 5,000 RPM in the little dynamotor inside, which has 2 outputs, as you might expect. It's got 28 volts for 2 series filaments, 2 12-volt series filaments of the 2 tubes inside, and it puts out about 340 volts at 40 milliamps, which gives you the 5 watt for the plate, which gives you the 5 watt output at a reasonable efficiency. The big knob in the center where you see brake, there's a little door. You can see there's a hinge on one side and just a cotter pin on a chain. And they were very careful about this, that anything you might lose, it would be put on a little string or a chain so that you didn't lose it in the ocean. So you'd pull out that little cotter pin, you'd swing open the door, and there was a reel of woven bronze wire. It's about, I've got to actually roll my hand here. It's about, it's between 16 and 18 gauge, not heavy. Of course, it couldn't be heavy because the kite or the balloon had to support it. And this was like the tool you would use if you were flying a kite and land. The big knob in the front was the brake. So you could feed the line out as the kite moved or the balloon moved away. And and once the wire was fully extended, you were strongly urged that if at all possible to put the full 300 feet of wire out, because the system was designed inside to match the output of the tube, was designed to match 10 kiloohms. Hang on, what's going on? Is some audio on there? Okay, anyway, it's designed to match 10 kiloohms and you wouldn't have the right impedance if you didn't wind all the wire out. In any case, you look, there's two other little knobs down there. One says ground. And so for the ground, you unscrewed that. It was it's a solid aluminum plug, weighs a couple of ounces, and you just throw it into the ocean. And behind it is 15 feet of this woven bronze wire. And the 15-foot in the plug itself allows the wire to drop straight down. So you've got a vertical 15-foot long ground into 3.5% salt, which is a very effective ground. The one on the other side, you wouldn't touch, because this is just, behind it's a cylinder of desiccant, which keeps the radio inside dry. Near the top, on the left, you'll see a little brown black thing, and that's the plug for the other feature of the radio. That's where you plug in your light so that you can use it to indicate your position at night. In the middle, on the right, there's a manual CW button there. So if the person using it happens to know CW, they can communicate specifically. On the left, the BC778, you'll see there's a switch in the middle, and there's 3 positions for radio, 3 positions for light. And next to it is a tune, and you can optimize the output. Well, how do you know what the output of the radio is and whether it's putting out anything at all? On the top, there's 2 little clear viewing ports that you can look into the radio, waterproof, of course. And under the one on the right side, there's a little incandescent bulb, the standard dial light bulb from the time. And when you bring the generator up to speed, it will light up, and you know that you're at the correct speed. On the other side is a little neon tube, which is connected directly to the antenna before it emerges from the radio. And you can actually watch CW being sent by, it's a typical little NE2 orange neon bulb. So you have the reassurance, and if you peak up the tune, then of course you'll see the bulb glow more brightly. So very, very simple and very, very reliable. Now on the other side, on the right here, is the CRT3, and this is the one used in the Pacific. And it doesn't have so many functions. We'll get to the functions in a moment, what you can send. Actually, the BC778 can fairly be said to be programmable, that you can basically choose among 4 or 5 different messages that you want to send out. The CRT3, it sort of has the complexity of switching back and forth every 30 seconds between 500 kilohertz and 8364. So you're sending both a medium frequency signal and you're sending a shortwave signal. So we'll get into a little more detail in a few moments. Okay, actually, we'll just briefly talk about it now. So this is the older 778, and you'll see that this can be programmed inside. That's why there's screws at the end of this little tag, because you can, this is something you wouldn't touch in the life raft, but the aviation mechanics who set up your unit would have put in whatever that particular unit wanted for their planes. And so here, if you set this to auto 1 with radio pointing up, then what you're going to get as you crank it is an SOS and a long dash repeating. And as obviously we all know the function of SOS, and the long dash is necessary because direction finding is very, very difficult on the CW signal, because your S meter or your direction finding meter is bouncing all over the place, where the long dash, of course, is just what you want. So you can turn your loop and you can find that narrow null, which says you're right on the bearing of the transmitter. There's also auto 2, which you could use. And this also has a long dash repeating, but you send prosine AA, di-da-di-da, di-da-di-da. And I would think there wouldn't be many of you out there that know what the prosine AA means. We'll get to that in a minute. If you want to switch this switch around 180 degrees, then you basically turn the radio off and you turn the signal lamp on, And normally the only choices you have for the signal lamp are continuous, and you can hand key it if you want to send a message to a plane above. And whoops, hang on. In the lower one here, let me just, I've got to move that panel up there. Okay, so this is a CRT3, and here there aren't quite so many choices. You can switch to 500 kc only and use the Morse key. And I can tell you, I've tried it, that if you're the only one on the life raft and you've got this thing between your legs, remember this face is pointing outwards, so you can't see it. So you're cranking vigorously, probably with your right hand, and you have to reach around the front, find that little key button by feel, and then you have to try to send a clean CW as you're vigorously cranking this thing that's wiggling around between your legs. But it does work, and I don't think you'll be graded on your keying if you get rescued. In the lower one, you have really just 500 kc manual. You can't send those the SOS and so forth up here. But what most people would have used is this automatic. In this one, you get 30 seconds of 500 and then 30 seconds of 8364. And for each of them, you'll get several SOSs followed by the long dashes for direction finding. And the bottom position here is you shut off the radio and you use the signal light. So the outputs then for the BC778 are that continuous tone, and then long 4-second dashes separated by 1 second key up. SOS, the AA Pro sign, and any mix of the above in the automatic position. So the thing was programmable, if you like, but all programmed back at the hangar, and not when you're out in the field. You wouldn't start trying to take the front panel off in a life raft. And of course, you could manually key. And the lamp really just steadily on or manual keying. And if you think about the fellows in the raft, it's quite easy to know when to use the light, because you'll keep using the radio until, let's say it's dark, poor visibility. Well, even in the bright daylight, you'll be listening the whole time for the sound of aero engines. And until you hear them, there's no point of going to the light. But if it's night, you just wait and listen and send out your RF. And if you hear aero engines, and I suppose you'd cross your fingers that there wasn't an enemy plane, you start the light. And you might think that the light, as you'll see in a moment, is nothing but a little pilot bulb, a little 6-volt one you've seen in any number of older radios, a watt or so, I guess. And you might say, well, what use is that out at sea with the search plane typically 2,500 feet above? Well, the lighthouses that we have now in Nova Scotia, the classic ones with the family living on the isolated island are all gone. But the ones that are in use, which have ranges of 15 to 25 miles, use a bulb which is identical in size and shape to a standard car brake light bulb. And no problem, 15 to 25 miles at night. It doesn't take a lot of power. So the little lamps are that they have here work very well. Oh, I just had to throw this in. The Russians, as I'm sure you're all familiar, have copied an awful lot of stuff that we've made over here. And this is a Russian copy, which they produced in some numbers of the BC778. Okay, now, as I think I mentioned earlier, this wasn't designed to only be used by the radio op out of the plane, because, you know, who knows who's in the life raft, anybody that could survive, and it might be a waist gunner or the bombardier or anybody. So everything you need to know to operate the radio is on the top. This is the top looking down, and the knob in the middle is simply the waterproof cover that's over the crank socket. And when you're ready to use it, you simply unscrew that and you put the crank in. And at the top here, you see these two clear lenses. And each of those lenses, well, on one side, as you can see here, speed indicator, keep lighted. So as you crank up and you approach the 80 RPM, there's a circuit cutout inside. So you're not wasting your energy putting out low voltages. You have to get up to the correct voltage. Then the cutout, the little voltage sensitive relay, cuts in, and you're powering the tubes. Once you apply power to the tubes, it takes 15 to 20 seconds for them to start functioning. So you can start this thing fairly quickly. It'll only take you a few seconds to bring it up to 80 RPM. And then you've got 15 to 20 seconds and it starts producing RF. And when it produces RF, you look into the little lens where it says radio output, and it's an Ne2 and it glows orange. And the more power you're putting out, the brighter it is. And of course, it follows the CW. So you can see what you're sending and you can see that you're sending. And it's tied in just before the antenna cable goes out to the outside of the case through a little rubber fitting. So if you're getting flashing a neon tube there, then for sure you're putting out RF. And if you're in any doubt, I suppose you could touch the antenna wire, but since it's 500 volts at 10,000 ohms, you get quite a tingle. I wouldn't want to. And you see under here, they've got the Morse code for somebody who doesn't know. They've got a little cartoon of exactly how to set the thing up so that you're basically, it's a little bit elaborate because you have to have insulated cable which ties the base of the antenna to a rubber oarlock, which is part of the raft. And you've got to have your metal ground over the side. But everything, you don't have to do any tying. There's alligator clips and there's little soldered loops and so forth. So it's very simple to put together. You certainly don't need any tools. There's one wrench, and it's for the crank in the center, because if a man's been in the sea for quite a while, his hands often will get softened by the salt water, and you might have trouble getting that off. So there's one wrench that does the friction drag on the kite reel on the front of the radio, and this move the crank socket cover so that you can put the crank in. Here's another picture of a fellow using it, and you can see this is basically what's involved, and it's really quite quick to set up. I put this in because I'm not sure if you can read it there, but they talk about, actually this little bit on this page is all they think you need to know to run this radio, and I think they're correct. The ranges down here shows you how important the ground is. That at sea, it typically will give you a distance of 250 to 500 miles. Inland lake, 50 to 150 miles. On the edge of a lake or stream, 30 to 50 miles. On land, grounded and moist earth, 5 to 10 miles. So this thing really needs a good antenna. And on the one I have, I've given a number of demonstrations, and I don't worry about, some of them were before 500 kilohertz was removed as an essential emergency frequency, but I didn't put any ground out at all. And it's still putting out enough, so if you put a World War II radio that tunes 500 kilohertz nearby, you'll get a nice signal, but it's not going to go very far. So ground is very important for these things. This is what it looks like sitting in your plane, your B-17 or B-24 or 29, whatever. And it's a big padded bag hanging on a hook next to one of the exits from the plane. The bump in the corner here is the kite, which actually is, its frame comes apart in the middle. So that's half the height of the kite. And here's the bits. This isn't a very military setting, but it was the clearest picture I could find showing what you get in this box. You get of course, in this case, it's a CRT3, and you can see you open that door at the front, and here's the reel of wire, the 300-foot reel, which is basically your antenna, and supported by either a kite or a hydrogen-filled balloon. And there's the crank installed. Here's the kite, 4-foot box kite. It goes together in a flash. Each of these halves, it comes apart in the middle. You just push the little aluminum tubes together, and they sort of jam in place. And hidden under the fabric is an X at either end to spread it out into the square shape. and it's all little articulations, and it folds flat, but then you just pull it out one motion and it pops out into exactly this square, so that you can put the kite together in 2 minutes. Below it here, these are that they give you spare reels of wire, obviously in case it breaks or it gets badly tangled. You've got more. Here's that wrench just for the 2 nuts that you might have trouble with. Here's the 2 tubes. Now these big gray jobs here, these are full of, we'll see in a moment, calcium hydride. And you put you open them up. Those of you probably remember, the older of you remember how coffee used to be packed. It would be in a vacuum sealed can like this, and there'd be a little key at the top, and you had to lift the key and break it off from the can, and then there was a little tongue, and you put it on and you wound around and you opened it. That's the system used here. So the calcium hydride has to be kept away from water, and when you open it, you hook up a system using these tubes to fill the balloons. And the balloons are also in cans because they're latex balloons, and latex will deteriorate with time unless it's in, I think these are in nitrogen, so they'll last forever. And in the bag itself. So and here's the great wide straps you put around your legs. So it's all nicely designed. And the light in here is to be worn on the head, pointing straight up when you're trying to draw the attention of a plane, or pointed in front of you when one of the very distressing things that often happens is that in a ditching, there's a lot of confusion. The plane comes crashing down in the water, and maybe some of the men are wounded or shocked. And people in the dark, especially, stuff drifts apart. And so you hear guys calling. And in the open ocean, if somebody's crying for help or to be located, it's very difficult to tell where the sound is coming from. There's wave and wind noise all around it. And it's very difficult in that huge open space. If you have a light that you can shine in front of you, you can find things like the floating water and food rations, or the waist gunner who's gone missing from the group. And so for both things, the light is extremely important. Now, some of them come with parachutes in them, on top of them. And at first, if you think about it, that doesn't sound like a good idea, because you're ditching in the ocean. Of course, the pilot's trying to put the plane down, get it as parallel to the water as possible. And the ideal would be to set the tail down first and let the nose then settle on the water. Because if the nose goes in first and you're going 100 or 120 miles an hour, it's like water's like concrete at 100 miles an hour. And the plane's probably the nose will break off, or at least the plane will flip over on its back, and total chaos inside, and probably won't be any survivors. So why would you have this? Because if you threw this out first, the plane might not settle on the water for another couple of miles, and you're never going to find it again. What they use these with parachutes for was if the plane that came, remember that the search planes are mostly unable to land on water. So they see a bunch of guys in a raft, and the best they can do is mark a position and report what they found. But as the war went on, they fitted these search planes with more and more equipment that the men could use. And so one of them was that if it appeared that the men didn't have a radio, they could just throw a radio out and hopefully get as close as possible to the raft down there. And so there's the white is a static line, and then you tie the static line to something in the plane, and then throw the radio out, and you see the 2 little pins, which you'll pull out when the static line reaches full extent. There's a whole thing here. This, by the way, this is a page from what the air crew had in the Second World War. Was every member of the crew, they had half a dozen different tasks, had a folder, and a ring type folder, and from time to time they get a pack of new pages, and it would say throw out pages whatever 6.3 through 6.8 of your present folder and put these in. And this is how they kept the whole air crew of every plane up to date with changes in technology, changes in enemy tactics, better ways to do things. And it's very interesting because I don't have a complete one, but I got a lot of these pages, and it's the government or the engineers telling the people how to use the equipment. And there's quite a few of these on the Gibson Girls. So it's how, whoops, that's how you find out a lot of it. Here's another way you'd use the parachute one. A long static cord means that you can, in many cases, the rubber raft is heaving and bouncing up and down relative to the plane. And I can tell you from 4 expeditions out to St. Paul Island, CY9, that when you're trying to get heavy boxes out of a boat into another boat, it's pretty dicey. So what you do is you give the guys in the raft the end of the static line. You just throw the radio in the water because it won't hurt it, and then they can reel it in at their convenience. Okay, here's a couple of others showing how you put the box kite. Even has 2 different places you can attach your wire, because one allows the kite to perform best at, I think it's 6 or 7 miles an hour wind up to about 15, and the other one allows you best performance at 15 to 35 miles an hour. So you pick the one that's around you at the moment. And here, as you can see, a little more detailed diagram of exactly how the radio is used. This guy, he survived his ditching really well. He looks pretty natty. Yeah, here it is. Here, just the corner of the kite. I have a kite here, but it's in pretty sorry shape. Whoever had the setup before me, I think, took it out and really used it. And it is actually, it's an excellent kite if you like flying kites. And here's the for the balloon system. And again, this is extremely important, because if you don't have a fairly brisk wind to get the box kite in the air, you can't use the radio unless you have this balloon system. And so again, the balloon is sealed in this can, and this can's been opened. They've used that little key and torn the metal all the way around. You can see here's your calcium hydride container, and then a special tube. You have to hold it in the water, underwater, because it generates a tremendous amount of heat, and the hydrogen boils up through and fills the balloon. And when it's full, they have a little system here. So there's a cork that pops in, and there's already basically a little clamp around the neck of the balloon, which goes to a clip to which you snap the one end of the woven bronze wire. And this of course is the thing being used. Let me just move this up. Yeah, okay. For the chemists amongst you, this is what actually happens. And you also want to be careful of it, because calcium hydroxide is just as strong a base as sodium hydroxide or household lye. So you hold it in the water, and once it's done its job, I presume you just let go of it and let it sink. Oh, whoops. Yeah. Okay. Now the British tried to get around it another way. Instead of going to hydrogen, they tried to figure out a way they could get the kite high in the air. And they came up with this business here. They took a very type signal pistol, and they built a little rocket that would be fired by the signal pistol. And to the rocket, they tied a piece of line that went to a kite in a narrow cylinder. And when the kite was yanked out of the cylinder by the rocket taking off, it was supposed to spring into its final conformation, and everything would be great. Apparently, most of the times that they tried this, the rocket would be thrown off course when it reached the end of this little tow line, as they call it here. And the first couple of times, apparently, it came right around 180 degrees and sank the life raft. And that wasn't exactly the result they were looking for. So I don't think this was ever put into practice. I hope not, for the British aviators' sake. Now here's the headlamp, which the first picture I saw, it looked a little silly with this guy with his light strapped on the top of his head, but it was hardly silly if you heard the drone of a rescue plane or some plane, and the light makes an enormous difference in night. Well, the raft is utterly invisible without it, and even that little light, and even here you see, as a backup, they give you a second bulb in case the first one burned out. And this just plugs into that little receptacle in the upper corner of the Gibson Girl. And here's just showing it in use again in a page from the standard manual that all the crew of the bombers got. And looking for people and precious things in the water, and for becoming located by a search plane. And yeah, I guess this pretty well describes it, that they could be worn both vertically and horizontally. And now this is the specs of the 778. So you get a feel for what it really is as a radio. And again, as we've said from the beginning, it has no batteries of any sort to die in storage or during use. The generators take 80 RPM arm speed and turn it into 5,000 RPM generator. They look like very much like those of you familiar with radios from the period. Most radios in aircraft had what they call dynamotors, and they take the 25 volt or 28 volt working voltage from any of the American or British planes and turn it into whatever you wanted, usually 240 or 350 or 600 volts to run the transmitters and receivers. And so the 778 puts out, I think I mentioned, 330 volts at 40 milliamps, which comes out to about 12 watts of plate power. And about 10 watts would go into the power oscillator, which we'll look at in a minute. And a little bit would go into the filaments and into the modulator oscillator, audio oscillator tube. And so the whole thing, it has a nice ergonomic shape and relatively low RPM and the wide belt to minimize the cranking lever. And also, when you're bringing the thing up, it is sort of interesting that you spin it faster and faster and you get to 80 RPM and the light lights up and you should stop there. But if you keep going, all of a sudden it gets very hard to turn. And they have a little governor in there. It's quite a clever thing with springs and two little arms which swing out due to centrifugal force and drag against a cylindrical piece of metal. So if you try to go too fast, which could, if you went fast enough, you might burn out the filaments there because, of course, your voltages go up with the speed. But as you get much above 80 RPM, it gets really hard to turn it. And so you naturally learn very quickly. You bring it up and the light lights and you just go to keep the light lit, and you have no desire to go faster. So you learn very quickly the speed to crank the thing at. Whoops. Okay. I think I've gone over most of this now. Yeah, and the fact that the modulation, so it has two tubes, one a power oscillator, the other a 1 kilohertz modulator, to give you these three frequencies, which broadens out what people can catch. In other words, in the day, just because the mechanical dial on your tube radio said 500 kilohertz, yeah, you might be 499, 498, 502, 503. But with these three, you have a much better chance of hearing the actual signal. Okay, this is a schematic. I'm not going to go through it in great detail. I'll just point out a couple of things of interest. One, you see there's a big connector here, and this divides everything on this side of the connector is bolted to the case itself. Everything on this side is on the circuit board or fastened through the front panel. So when you take the front panel off, you just disconnect this big Jones connector, and it's very easy to work on. And down here, there's some interesting things. In the case, of course, here's your gear reduction. Here's the generator, and here's this cutout I was mentioning, so that this doesn't pull in till the gen is up to the correct speed. And over here, you've got these three plastic discs that are, well, they're molded together into a single disc, but there's all the bumps necessary to send the SOS and another set for the the AA, and another set for 4-second dashes with 1-second gaps in between. And this is for what's called the auto alarms that many planes and ships had at the time. And the value of the auto alarm is that it's, well, let me just, I'll come back to that. We'll do that in a minute. And then there's a switch cam down here, which decides which of these you use. And this here is actually the programmable part of the thing, that by mixing and matching where these connections are made to these connections, you can choose what the message will be that comes out of the radio. Okay, here's the power oscillator, and you know, I expected the first time I opened one to find a big fat 500 kilohertz crystal in there, but they didn't use a crystal. And it's actually a sort of a coal pit circuit here. And I'm pretty sure the reason is that these things get slammed and knocked around, and a fairly large 500 kilohertz crystal is going to be a bit fragile. So I think they just avoided crystal and used a, as they say, a coal pits type circuit. And here's the tank. Here's the capacitor for the tank, and this is what you tune when you tune the antenna. The loops here are that's the 300 feet, and here's the 15 feet that goes into the seawater. And here's your little neon tube. So if your neon tube is lit, then you've got power to your antenna. The blocking capacitor here, you wouldn't want to have that not there, because you're getting 340 volts DC here, and that you'd have 340 volts DC on your antenna out here, which you're handling. So that wouldn't be a good idea. The one of the challenges was that it's not just the same 300-foot antenna every time. If you're using the box kite and it's a high wind, the antenna is going to be down at maybe as low as 10 to 15 degrees off the water. So instead of a vertical, you've got an antenna that's sloped way down, which there'll be all sorts of capacitance between the wire and the water, of course. So you're going to have a very different value for these two capacitors in the tank. And so they got a clever little system here. You can actually see it in the photo in a minute. So that a full turn of the tuning capacitor on 180 degrees, the fixed capacitor beside it is switched in. And on the other 180, the fixed capacitor is switched out. So it gives you in the end a very broad range from just a few picofarads up to, I probably by the look of the caps and the values, 800 or 900 picofarads. So you can pick what matches where your antenna is in relation to the water. On the other hand, if you're using a hydrogen balloon, then you have little or no wind, and it's going to be a true vertical. It'll probably be close to 90 degrees, or at least better than 70 degrees. So, you know, the engineers had to think of these things because they had to have it work in all weathers. Here's the back of the front panel. As I say, half of the guts are here. And for instance, there's the tank coil there, dipped in some kind of sealant, which makes them very resistant. And I noticed that unlike a lot of the military gear, all the capacitors are micas, which is great because if you get one of these things, you usually turn the crank and they work just fine. There's no old wax paper capacitors to go bad. And two tubes, you can see, of course, they've kept in the socket by some springs. There's the other tube over there. This is, I think, the 12CS7, and this is the 12A6, which is the power oscillator. Here's the antenna tuning cap, tank tuning cap, and you see on the top here, you can actually see the circuit. Here's the fixed capacitor that's in parallel, and here you have 180 degrees where it's connected in parallel. When you swing this around to the other side, of course, this disconnects, so this drops out of the circuit, and you only have the capacitance in this. And they even gold-plated the cap for good measure here. And there's the function switch there, and there's the seal outlet that goes out for the light. And here's the other half of the electronics, and this is the what's fastened in the case. And at the top here you have the lamp, which shows, and above it, where you can't see it, is the little window, so you can see, look through the window, see whether this is glowing or not, so to know whether you're on speed. Over here is the little neon, and it's got, as you can say, a 50K resistor in series with it, so you're not loading down the RF, you're not wasting much RF. Here's the magic governor that doesn't allow you to go much over 80 RPM, that as it speeds up, and this is spinning at a couple thousand RPM. It's picking off its speed off this great big gearbox here. And of course, here's the generator down here. And so this prevents you from overspeed. And here's through the three separate quote unquote programmable, all the information is molded into this plastic hub. And this, of course, you're opening and closing contacts to send the various CW messages. And here's the EEPROM, let's call it the EEPROM here, that these four wires can be shifted on those four screws. The screws are 1, 2, 3, 4. And of course, this is 5, 6, 7, 8. You can switch them around. There's a little chart in the manual that tells you, well, if you want, excuse me, this message, you'll rig up this, again, something done at the hangar, not out in the Pacific or the Atlantic. Here's the cutout relay. Let's see, I mean, gotta move stuff around so I can, yeah, okay, that's most of what's there. Just a quicker look, here's, you can see the numbers there. So you look at the table in the manual and you decide what messages you want the thing to send when you turn the crank, and you set it up there. Here's the Pacific one, the dual frequency. And here they've done away with a lot of the basically options. So you've got a single basic message on this single hub for the 30 seconds 83 and 30 seconds 500 kilohertz. But similar functions. There's your gen light, and here the neon bulb is connected to the other half of the radio, the faceplate. Now, another way you can make this thing more effective is, as you probably know, at the time of the Titanic, the ITU met and they put in a whole slew of new safety features. And one was this clock here. And this is a radio room clock, as most of you probably know. And basically the law reads, it read in 1912 and it reads today, that these times are quiet times. And so from 15 to 18 minutes of each hour and 45 to 48 minutes of each hour, on 500 kilohertz at least, you're supposed to not transmit unless you have an emergency, and you're supposed to listen for anybody who does have an emergency. So this at least allows the men in the life raft that if they're, you can't crank it all the time, it'd be too exhausting. But if you're going to crank, then do it in those 2-3 minute periods. And since most aircrew wore a good watch, that wasn't hard to figure out. This is what the German clock over here, if you look at it, is exactly the same thing. They were doing exactly the same thing. And the one in the middle is a post-war clock. And this has those two green wedges, which is a second emergency frequency came into use 2182 kilohertz. And it was used by, anyway, well, all sorts of ships in all sorts of situations. So this made your 5 watts more useful because you weren't competing against 100-watt radios in the same area, and people were specifically listening. Now, these dashes outside here are another quite nice thing. This was one of the signals that the BC 778 will put out, 4-second dashes spaced apart by 1-second intervals. And 4 of those 4-second dashes with the 1-second intervals will trigger a device called the auto alarm. And at the time, almost all ships would have it, and almost all search planes, not necessarily every plane. And so there was a little electromechanical device with a fixed 500 kilohertz receiver, and it was on all the time, so you didn't need it tended by a radio operator. And if it received 4 of those dashes with the correct space in between and the correct length dashes, it would set off lights and bells and so forth. So there'd be an automatic announcement if somebody was sending this pattern and it was received by the receiver that was with the decoder. And that worked very well. An awful lot of, you know, you can imagine being a radio operator that spent a 12-hour shift listening for faint SOS signals or faint 4-second, 1-second gap signals. Anyway, so this is a early bit of automation, which was apparently very, very effective. Okay, remember that fused AA? Well, I got curious. What is, you know, da-da-da-da, da-da-da-da? What is it for? Why would they put it? Clearly, it had to be something important. And so this is what I fished out, looking in all kinds of sources. Of course, the pro sign, the fused, are the ones with the bar over, and there's 5 of those. In the end, we discovered that it was for unknown station. And at first I said, what? Why does that make sense? Well, it also means a station with no call sign. And the only kind of station with no call sign was an emergency transmitter at the time. So it tells you that if you get da-da-da-da, da-da-da-da, that it's coming from either a Gibson Girl or something very similar, an emergency transmitter. This was where I got it out of a, and this is kind of interesting. I'm not going to go through all this, but these are the pro signs that a military radio operator, certainly an aircraft radio operator, would have learned when he learned the Morse code in the Second World War. And some of them, of course, we would recognize today. A lot of others, like fused HM, da-da-da-da-da, for emergency silence. And whether this was to discourage DF by the enemy or something else, I don't know. But there's a number that we wouldn't use today, some that we do. This was just an ad that I thought was interesting from Belden Wire that made that very nice, strong, woven bronze wire. And it's saying, which is true enough, that, well, here, I'll read you a little of it. The hopelessness of waiting on a cruel sea for days or weeks with help just over the horizon will probably not be experienced by another crew from another disabled bomber. Now emergency life rafts are equipped with radio transmitters with a kite and a length of antenna wire. Now a call for help will travel over the seas to friendly ears, and the shipwrecked have something more reassuring than a bare hope of rescue. And anyway, that's written for the public, of course, but it was something that helped the morale of the air crew, because being drowned at sea wasn't a very attractive. And this gave them hope that, yeah, we'll start cranking and people will hear us. And as you saw in the numbers at the beginning, almost 4,000 air crew were saved by the use of this and similar things. This is a Goldfish Award, and if you went in, you went into the drink, then it was sort of semi-official that somebody thought it up, not the Department of Defense, but guys would wear it with pride, you know, say, I went into the drink, we had to ditch, and I survived, and here I am. These are some of the planes. Here's a German one, just a little Heinkel pontoon plane, and presumably a couple of German flyers there that they would come out. The Brits had a boat quite similar to the PT boat at the time, and this was, you didn't want to go in with a great big ship or something slow and clunky, because the Germans would watch, and if they saw a plane go in and a life raft there, they would know that the Allies would send something after them. And there's a number of incidents where a PBY came in, and the Germans were waiting just kind of over the horizon. And once the PBY landed to pick a couple of guys up, they would go in and shoot it to ribbons. These boats, actually, just to get a little off the story, were something that was developed after the war. And there's a service in Britain called the RNLI, the Royal National Lifeboat Institute. And they've rescued thousands of people from the 1880s to the present. And they've got very sophisticated boats for going out from the English coast and rescuing sailors and people from private yachts and so forth. Anyway, these were fast, and they'd get in there, pick the guys up and get out of there quick. What also came in, the PBY Catalina was a great thing to pick them up, because but still in rough water, it often couldn't come in. So what they ended up doing, and this was just at the end of the war and after the war, here's a B-29. It's got this huge, they had boats and they had life rafts, and they'd strap them to the bottom of the plane, and they'd go in and see a couple guys in a little flimsy thing like in the next picture. They would drop this, and it would have a radio, usually the Gibson Girl, and it would have, you know, water, food, it's called medical supplies, and it gave the guys much longer time, because out in the Pacific, you know, they could be thousands of miles from assistance, and so a boat would have to spend some days getting to them. So this was a way to basically give them what they needed to stay alive till they could be rescued by either a plane that could land on the water or a ship. The Brits came up with a sailboat, and they dropped the whole boat in there. Here's one coming down through the air. And so I'm sure there's some British aviators who had nice stories to tell about flying off to war over Germany in the morning, getting shot down and ditching in the water and sailing home. And these actually had the Brits bolted a Gibson Girl in, so you didn't have to hold it between your legs. It was the boat was rigid, and so they'd bolt it in a place where you could conveniently crank it, and that made life a little easier. And they often had a little minimal TRF radio with a battery for the receiver, and just like three tubes, so it didn't use much juice, and a little battery, and so you could actually have two-way communication. Here's a B-17. You can see this is still a warbird. They still have, after a while, they dropped the ball turret and basically all the guns, but this still has that. And you can see the boat strapped to the bottom. And here's, this is in the Pacific, and this was just after the war. They left some of the B-29s out there, and they got this orange paint job. They stripped out all the guns, etc., and either had a large raft or a boat strapped underneath that they could drop to people in trouble. Here you get a little better look at one of them. Another look. So this isn't a weapon up front. This is a radar dome, and that could help in the search as well, of course. And I mentioned that these Gibson Girls were built by the Bendix company of North Hollywood. Well, they were probably chosen because they are already building the direction finding equipment that would be used to locate a Gibson Girl in a raft somewhere. And so I just wanted to give you a quick intro to how they would direction find. This is, of course, is a highly directional loop. You can't really see in this picture, but you see there's a small word front there. There's a fine groove underneath. And so this would be bolted to either the belly or the top of the fuselage of the plane. And this would be inside the plane. You see there's a crank, and this opening here used what we would call a speedometer cable, the same thing that older cars used. And so you'd crank this, and this would turn, and this was calibrated. So when it was flat like that, in direction, the direction of the long axis of the plane, then this would be set up at 0, and there's of course 360 degrees in here. So you would turn this, and you'd be listening on the radio equipment I'll show you in just a moment. And the loop, what you wanted was the maximum signal was off the broadside, and it was very broad. So you couldn't tune for max. It wasn't nearly accurate enough, but you got a sharp null when the signal was coming at the end, one end or the other of the loop. Now, of course, there was a problem that each end would give you a sharp null. And so you either knew the frequency exactly or you were 180 degrees out. But in most cases, for instance, you'd be taking off from land, and you knew that the transmitter, the rescue transmitter, wasn't on land, so it had to be in the direction out to the sea. And anyway, there was a number, and there was other ways you could tell the correct from the incorrect setting. But they crank this till they got that null in the correct direction, and then they could tell the navigator or the pilot that there were 60 degrees from the bearing of the plane, and the nav would know the bearing of the plane, and he could figure out exactly the bearing that the emergency radio signal was coming from. So pretty simple, but it worked fairly well. This is looking at some more of the hardware that if there's any surplus hounds out there, I'm sure you've seen some of this. It was quite common. But this was the receiver. There was a MN 24, 25, 26. There's a whole series of them. And this was something that was tucked in the corner of the plane, and it would be controlled by this little center here. And if you look at what's on here, this could be a magnetic compass or a direction finder. And so on here you see it's off, compass, receive antenna, which would be a wire antenna, and receiving loop And you've got 3 bands here that go from 150 kilohertz up to 1500. So you've got your 500 in the middle. You put on the receiving loop, and it was often on a panel like this. And here you've got this, you would tune, you would adjust the gain. So the signal you were trying to follow would be at max. And as you turned the loop and you got the minimum, the needle on that meter in the center of the large panel on the right would dip down, and the position of the loop would be recorded on this large gauge on the right side with the long needle and the fine graduations. So you could basically get quite a precise, within a degree or two, the exact bearing on the desired signal. Anyway, I won't go into any more, but that's so the people that designed this system, and these Bendix systems were quite good. They're still building all sorts of marine stuff. My daughter has a fairly large boat, and she handed me a Bendix autopilot to fix, and I'd never seen one before, so it was a challenge. So the people that built the direction finding system built the transmitter they were trying to find. There's another little one that pretty well all planes in the war, certainly all American and Canadian ones, had what they called the command sets. 2 million of these command sets were built by the Aircraft Radio Corporation of Boonton, New Jersey. And this one, like a variety of them, had a standard antenna, which was on top of the fuselage, usually to the tail. And you see the 2 little L's there. And that's for the directional loop. And there's a switch down here or for antenna or loop. And so these went 190 to 550 kilohertz. And they could be used, they're mostly used for finding an airport beacon to get the plane back to its hangar. But they could also be used, and were also used, for, and this tuned 500 kilohertz, and could be used to locate a plane, excuse me, a raft with a Gibson Girl in it. And this is just the standard receiver that was in virtually all multi-engine planes of the US and Canada and some of the British planes, BC 348, which I'm sure some of you have seen. And it was interesting because they had a whole series of models, and this was the L. They started at A. A and B didn't have a low frequency band, and immediately the Army said, no, we need the low frequency band. So after that, they all had a 190 to 520 KC band at the bottom. And so you could, and this is what distress signals would often be heard of first, because this is the radio that sat in front of the radio operator in B-17s and B-24s and so forth. This is a picture taken at the time. Here's a captain of the ship. It was called the SS Hope. It was a brand new hospital ship that in early 45 was sent from the West Coast out to the Philippines. It was sent to pick up a load of wounded soldiers from the fighting in the Philippines. And these 4 fellows were on quite a different mission. They were the crew of what they called Dakota, and they were flying from one tropical island to another, quite a long distance. And they got out, and they had a load of radar equipment in their plane. They got out, and several hundred miles out from their origin, they ran into a large, violent thunderstorm. So the pilot took them around the storm. But by the time they got around it, they were rather low on fuel, and they could no longer hear the homing beacon from either the airport they left or the airstrip they were going to. So they just ran out of fuel, went into the ocean, got out. So they were 4 or 5 days. They started cranking on the Gibson Girl, and the Hope, the Hope ship here, was about 800 miles away. So they had the CRT-3, and clearly the 500 kilohertz didn't help, but their 88 megahertz signal did, and they were picked up. And apparently it was kind of nice because there was a couple of hundred nurses and 0 patients because they hadn't gotten there yet, so they were treated very well. And here's another group from a B-29. A B-29 had a crew of 10, and these guys developed engine troubles, and they were way out over the Pacific, and they finally found a little island. There's no airstrip, there's nobody on it, and they tried to land on the beach, but the beach was too narrow, so they had to go into the water next to the beach. So they got ashore okay, but they probably wouldn't have been found, or not found for a long time, but their Gibson Girl got them located. This is a picture from a video of taken when the rescue ship came up alongside a life raft, and you can see here's the Gibson Girl that the guy's been cranking, and this one I guess is trying to pull down, I don't know if it was a kite or the hydrogen balloon, but anyway, getting the kite down. And so very happy to see rescue on shore. And this is, as it says here, AAF Emergency Rescue Squadron. This was in England, and they like to brag about how many downed airmen they had rescued, which was at this point 262 by this particular group. And that's it, folks. I hope you learned a thing or two from it. I find the whole thing quite interesting and kind of a positive thing. It's not the blood and guts of the war. It's attempts to save people.
Well, what a great presentation, Fred. And you know, as we were talking the other day, the ingenuity of those engineers and manufacturers to figure this all out, improve it, and mass produce it is just incredible.
Yeah, and they didn't have much time to do it either, but they were smart. They used real world engineering. They forced people to do it under the same adverse conditions that the downed airmen would have.
I got a quick question. The boat that they dropped, would it have a parachute attached to it? I mean, it's going to hit the water hard.
Yes, if you remember the British one I showed, the sailboat there, it had 3 chutes on it. And yes, the other ones had chutes too.
Okay.
Well, imagine if it landed on top of those guys in the water. That wouldn't be good either.
Thank you.